All right, welcome back. Today we're going to really dig into the laws of induction. We're looking at a classic chapter, trying to get past just the formulas.
Yeah, absolutely. We want to get to the core physical ideas because when you mention electromagnetic induction, everyone jumps to Faraday's law, right? EMF equals minus di phi dt.
Exactly. The flux rule.
But the crucial insight here is that this single equation actually covers two totally different ways things can happen physically. It's not one phenomenon.
And understanding that difference is, well, it seems like it's key to really getting electromagnetism. The goal isn't just the flux rule, it's seeing how it all ties back to the fundamental force law.
The Lorentz force. $5 equals Q plus V times B. That's the bedrock. That equation has to explain everything, even the tricky bits we're about to get into.
Okay, so let's start with that famous flux rule. Mathematician, simple idea.
Yeah.
Change the magnetic flux through a loop, and you get a voltage and EMF around it.
Right, and it works beautifully in like 99% of cases you encounter in basic circuits. The math holds up.
But the physics underneath, that's where the nuance is.
That's it. Feynman really forces us to see the two distinct causes baked into that one rule.
So, case one.
Case one, the wire, the conductor, is moving, but the magnetic field, B, is staying put. It's constant.
Okay.
So the charges inside that wire are moving with velocity $5 through the field by dollars. They feel force, the $5 times B by part of the Lorentz force. That pushes them along the wire. That's your EMF.
So a mechanical force, really. Motion through a field.
Precisely. Now, case two. The wire isn't moving at all. It's stationary. But the magnetic field itself is changing in time.
Ah, okay. So d by dt isn't zero.
Right. And Maxwell's equations tell us that a changing B field must create an electric field, an E field.
An induced E field.
Exactly. And that E field is what pushes the charges around the stationary wire. No $5 times B involved here. It's purely the dollar part of the Lorentz force.
Two totally different physical mechanisms, both described by the same flux rule.
Yeah. And that's why just blindly applying the flux rule can sometimes, make you miss what's actually going on, which leads to the so-called paradoxes.
Right, the exceptions that prove the rule. Or rather, show the limitations of the simple rule. Let's talk about the rotating disk, the homopolar generator idea.
Okay, yeah. So imagine a flat conducting disk, like a copper plate, spinning around its center. And it's sitting in a uniform magnetic field pointing straight up, perpendicular to the disk.
Okay, spinning disk, steady B field. We hook up wires, say, one to the axle and one to the outer rim to make a circuit.
Now, if you try to calculate the magnetic flux, Φs, through that circuit, well, the B field is constant. The area isn't really changing in a simple way that makes the flux change. Depending on how you draw the loop, the flux might even look like it's zero or constant.
So the flux rule, dV phi U, would predict zero EMF.
It seems like it should, but you definitely measure a voltage. There's a real steady EMF between the center and the rim.
So
it's purely the $5 times B Bale force again. The charges in the disk are moving outwards, or rather circularly, with velocity dollars through the fixed B field. That force pushes charge radially, creating the potential difference. It's entirely about the motion of the conductor. The flux rule, applied naively, kind of misses the point there.
Okay, that one's cleared up by $5 times B Gould. What about the other example, the rocking plates? That one seems even weirder.
It is subtle. Imagine two parallel metal plates hinged at one end, and they rock back and forth, opening and closing like a clamshell within a uniform magnetic field.
Okay, so the area between them is changing significantly.
Right, and you connect a galvanometer, a voltmeter, with wires that run outside the region where the plates are moving. So the meter and its wires are stationary.
Now, the area is changing, B is constant, so the flux flee through the loop formed by the plates, and the meter connection is definitely changing a lot.
So the flux rule, Nadelmatter, predicts a big oscillating EMF should be measured by the galvanometer. But you measure nothing, zero EMF, if those connections are truly stationary and outside the moving region.
How can the flux change so much, but the EMF around that path be zero?
Because the EMF fundamentally is the line integral of the total force per unit charge around the loop. That's E plus V times B CIISACS. The flux rule is a shortcut for this integral. In the rocking plates case, yes, there is an induced E field in the region where B is changing or where the boundary moves. But if your voltmeter's path stays outside that region, the integral of that specific E field along that specific path is zero. The Vol times B part is also 0 along the stationary wires, so no net EMF around that chosen path.
So the flux rule gives the total change, but doesn't tell you where the induced field is. You need the full Lorentz law.
Exactly. The physics is always local. Wa$ equals Q at plus V times B tells you the force on each charge right then and there. The Flake's rule is convenient, but it's not the fundamental physical cause in the same way. It averages things out.
Okay, so if we want to really isolate the effect of a changing B field, creating an E field, without any moving wires, $$ times B confusing things, where do we look?
Well, that brings us to a fantastic piece of technology, the betatron. It's basically designed to exploit exactly that phenomenon.
Right, the particle accelerator. It speeds up electrons, doesn't it?
It does. It accelerates electrons to very high energies, keeping them in a circular path. And the key is it uses a magnetic field that's specifically designed to change in time, and it's symmetric around the center axis.
So how does the changing B field accelerate the electrons?
Because a changing magnetic flux through the center of the electron's orbit induces an electric field, and this E field points tangentially exactly along the direction the electron is moving, so it constantly pushes the electron, making it go faster and faster.
Okay, that's the acceleration part. But a magnetic field is also needed to bend the electrons into a circle, right? The centripetal force.
Precisely. So the magnetic field has to do two jobs simultaneously. The changing flux in the middle creates the accelerating E field, but the magnetic field at the orbit radius itself has to provide the G times B$ force needed to keep the electron on that nice circular track.
That sounds tricky. As the electron speeds up, doesn't it need a stronger B field to keep it bent in the same circle? But the changing field is also accelerating it. How did that balance?
That's the genius of it. There's a critical condition. For the electron to stay in an orbit of a constant radius while it's being accelerated, there's a very specific relationship required between the field at the orbit and the average field inside the orbit.
What's the relationship?
The average magnetic field inside the orbit must be exactly twice the magnetic field right at the orbit radius,
Right,
the text orbit.
Exactly twice.
Exactly twice. If that condition isn't met, the electrons will spiral either inwards or outwards and hit the walls of the vacuum chamber. It's a beautiful piece of applied physics, relying entirely on harnessing that induced electric field from a changing magnetic field.
Amazing. Okay, so that's high-energy physics. What about something more
Yeah.
everyday, like power generation?
Well, the standard alternating current generator uses the other aspect of induction, mostly the Vi$ times B buyer part, but in a rotational way.
How does that work? You have a coil of wire spinning?
Yeah, typically you have a coil of wire rotating within a fixed uniform magnetic field. As the coil spins, the angle between the coil's surface area vector and the magnetic field lines changes continuously.
And that changing angle means the flux through the coil changes.
Right. The magnetic flux passing through the coil goes up and down sinusoidally as it spins.
So Faraday's changing. Then Faraday's law, math calculating GFE kicks in.
Exactly. A sinusoidally changing flux induces a sinusoidal EMF. If Philadelphia varies like cosine, the EMF varies like sine, where Montebille is proportional to omega t, where d is the rotation speed. That's your AC voltage.
And that drives an alternating current.
Yeah. And, importantly, the electrical power you get out doesn't come from nowhere. You have to do mechanical work to keep that coil spinning. The magnetic field exerts forces, torques, that resist the rotation, and you have to overcome that resistance. Energy is conserved.
Okay, so we've seen induction from moving wires and changing fields. Now let's shift focus a bit, away from the fields in space and more towards the properties of the circuits themselves. What happens when changing currents interact? Let's start with two circuits affecting each other, mutual inductance.
Right. Mutual inductance, usually written as math frank, is all about coupling. If you have, say, two coils of wire near each other, coil 1 and coil 2,
Okay.
if you change the current flowing through coil 1, island 1, that changing current creates a changing magnetic field.
And that changing field spreads out.
And some of its flux links through coil 2. So coil 2 sees a changing magnetic flux, and by Faraday's law, an EMF, Math-2, gets induced in it.
So the voltage in coil 2 depends on how fast the current in coil 1 is changing.
Exactly. The induced EMF, Math-2, is proportional to the rate of change of current in coil 1, di1 dt And that proportionality constant is the mutual inductance, Math-2. So Math-2 and di1 dt.
What determines how big Math-2 is? The currents?
No, that's the key thing. Math-2 depends only on the geometry. The shapes of the coils, their sizes, how many turns they have, how close they are, their relative orientation, all purely physical arrangement stuff. It doesn't depend on the currents themselves.
Interesting. And is the effect symmetric? Does changing current coil 2 induce the same kind of EMF back in coil 1?
It does. And remarkably, the coupling coefficient is exactly the same. Mathfrak is always equal to mathfrak delta. That's called the reciprocity theorem. It's not obvious why it should be true just from looking at coils, but the math works out.
Okay, so that's mutual interaction. What about a single coil? Can a changing current in a coil affect itself?
Absolutely, that's self-inductance, usually denoted by dollar.
How does that work?
Well, any current dollar flowing in a coil creates its own magnetic field and therefore its own magnetic flux linking through the coil itself.
Right.
So if you try to change that current dollar, you're changing the coil's own magnetic flux. And by Faraday's law, that changing self-flux must induce an EMF back in the very same coil.
An EMF that opposes the change you're trying to make.
Precisely. It's called the back EMF. The formula is mathkalo ddl T. The dollar is the self-inductance, again, depending only on the coil's geometry. And the minus sign shows it always opposes the change, dado ADT.
That opposition sounds kind of like inertia in mechanics. Is that a good analogy?
It's a perfect analogy. Think about mass. Mass resists changes in velocity,
Right.
equal with dt dl dollar, common acceleration. It gives things inertia.
Right, Feynman a dollar.
Well, self-inductance provides electrical inertia. It resists changes in current. If you try to increase the current, the back EMF pushes against you. If you try to decrease the current, the back EMF tries to keep it flowing.
So dollars is like the electrical equivalent of mass.
In many ways, yes. It measures the circuit's opposition to changes in current flow. For simple shapes like a long solenoid, you can calculate Lawler directly from its dimensions, number of turns, area, length. It's a physical property of the device.
Okay, if Lawler dollar is like electrical inertia and it resists changes in current, that implies you have to do work against it to get a current flowing, just like you do work to get a mass moving.
Exactly right.
So where does that energy go? When you've established a current dollars in an inductor, where is the energy stored?
The energy stored in the inductor is given by $1, Frac 1.2, Li22.
Ah, look at that. It looks just like kinetic energy, $1 frac 1 2 meo d22.
The analogy holds perfectly. Dollars like mass, Lawler's is like velocity. The energy you put in to establish the current gets stored, ready to be released if the current changes.
So is the energy stored in the coil, in the wires.
Well, that's where the calculation using Dowador seems to place it. But Feynman pushes us to think deeper. Where is the magnetic field?
It's mostly inside the coil for a solenoid, but it also extends outside, filling the space around the wires.
Right. And the more fundamental view is that the energy isn't really stored in the matter of the wires, but rather it's stored in the magnetic field itself, distributed throughout all the space where the field exists.
How do we connect the Li22 energy, which seems tied to the circuit component, with this idea energy spread out in the field?
There's a formula for the energy density in a magnetic field. It tells you how much energy is stored per unit volume of space, and it's proportional to the square of the magnetic field strength, B22. Specifically, it's Frac 1b, or a Frac 1c2 B22.
Okay.
If you calculate bar dollars everywhere in space, due to the current dollars in the inductor, and then you integrate that energy density Frac B22 over all volume, you get back exactly Frac 1222.
Wow. So the two views are consistent. The energy is fundamentally in the field.
That's the deeper physical picture, yes. The energy resides in the configuration of the electromagnetic field in space.
And if we go back to our two coupled coils, with mutual inductance, mathfrak, how does the energy storage work there?
You just have to account for everything. The total energy stored is the energy needed to build up the current IR in coil 1 against its own back EMF, plus the energy for $2 in coil 2 against its back EMF, plus the energy associated with the interaction between them.
So it would be.
It comes out to be $1 Frac 1.2 L1 I12 plus Frac 1.2 I22 plus math Frac I1 I22. That last term, the mutual inductance term, accounts for the energy stored in the field due to the interaction between the two currents. Hashtag tag outro. So wrapping this up, it's been quite a journey through just one chapter, hasn't it? We've seen that Faraday's law is really two effects in one hat, ultimately unified by the Lorentz force Vi dollars equals Q plus V times B.
Right, and we saw how that plays out from the paradoxes like the rotating disk to the incredibly precise engineering of the betatron.
Yeah, that Babby text orbic area condition is just beautiful.
Then we got into inductance, Liller and mathfrak, as circuit properties measuring electrical inertia and coupling.
And finally, realizing that the energy, Li2 lab 2, isn't just in the inductor, but is fundamentally stored out there in the magnetic field itself.
It really ties everything together. Well, thanks for joining us on this deep dive into the fundamentals of induction. It shows how looking closely at even familiar laws can reveal so much more depth.
Absolutely. And maybe something for you listeners to ponder. We saw the energy for two coils is $1 frac 1 2 L1 I12 plus frac 1 2 plus math frac I1 I22. Now, energy has to be positive, right? You can't get energy for free.
Right. It costs energy to build up fields.
Well, the mathematical condition that this energy dollar must always be positive, no matter what currents I dollars and I32 you choose, forces a purely geometric constraint. It demands that the mutual inductance mathrac can never be larger than the geometric mean of the self-inductances. Mathrac must be less than or equal to square root 1L and 2.
Huh. So the way you can possibly arrange two coils in space is inherently limited by energy conservation.
Seems so. It's not obvious just by looking at coils, but it's a deep mathematical requirement stemming from physics. What does that fundamental limit on coupling tell us about the possible geometry of electromagnetic systems? Something to think about.
Indeed. Food for thought. We'll catch you on the next deep dive.